Now that we're getting into talking about energy and how energy flows, then we need to talk about three main ways that we study heat flow depending on what's happening in the system. So the three main ways that we're talking about heat flow are heating and cooling, which is exactly the same as the way you think about heating and cooling already. We'll just look at the energy involved. The next one is looking at phase changes. We've already talked about these before. So what we are talking about with phase changes are this process of either freezing a liquid or thawing, melting. Maybe I'll use melting. So this is our transition between a solid and a liquid, and we can go either direction. We also have evaporation or vaporization. And the opposite of evaporation is condensation. And this is the process of going between the liquid and the gas phase, either direction. And then we can also go directly between solid and gas, and that's called sublimation if we go directly from a solid to a gas. And if we go the opposite direction, it's called deposition. So that's between our solid and our gas phases. So we'll look more at those in a little while. And then the third set of places where energy flows in the form of heat, and we talk about exothermic and endothermic reactions, is where we have chemical and physical reactions. And these are separate from the phase changes. I know phase changes are also physical reactions, but when I'm talking about chemical reactions, I'm talking about those classes of reactions that we've already talked about. So precipitation reactions, acid-base reactions, redox reactions, including combustion reactions. So these are the most common chemical reactions that we're going to talk about. And when we're talking about physical reactions, in addition to phase change, we can also talk about things like mixing and dissolving. And even though you don't normally notice a lot of energy flow when you do things like mixing or dissolving, there can actually be a significant amount of energy that is involved in these processes, and probably in a few other ones as well. Crystallization is part of freezing, and all of these involve energy. But these more subtle ones also can be important, and so I'm including them as part of our category 3. So in this video, we're going to focus on this first one, heating and cooling, but there are changes in enthalpy in all three of these major categories. Enthalpy changes are involved anytime heat flows in or out of a system. So we're going to spend some time talking about heating and cooling because that tends to be the one that's most familiar to us in terms of putting energy in or taking energy out. So I'll make a major heading here. All right, so when we are increasing something's temperature, you might think of something like boiling water on your stove, or if you take a pan out of the oven. So think about a pan coming out of the oven, and imagine two different scenarios here. You've got a cookie sheet that's made out of metal, and then you have your ceramic Corningware pan. This is sort of a cutaway version. There we go. So This is your 9x13 Corningware to make a casserole in or whatever. So whether or not they have something on them, you can imagine the cookie sheet without the cookies on it and the Corningware without the casserole in it. And if you take the cookie sheet out of the oven and you take the Corningware out of the oven, and let's say they started both at, I don't know, a 350-degree oven or something like that. It's not going to take very long for the cookie sheet to come to room temperature, and you'll be able to handle it. The Corningware will take a lot longer for it to cool. So why is that? So this is because different materials, they store heat energy in different ways. They also are able to transmit heat energy in different ways. So let's put that as a piece of information here. Different materials store heat energy in different ways. Some materials require only a little energy in order to raise their temperature. Other materials require more. And heat flows well through some materials. And it turns out that they go well through conductors, so metals typically. Anything that conducts electricity well generally also conducts heat well. And the heat flows poorly through insulators like ceramics and plastics. So conductors are metals. Insulators are things like ceramics and plastics. Anything you would think about being involved in an electrical circuit, those are conductors. Anything that you would think about that would help you grab something out of the oven. So cloth is an insulator as well. Paper, cardboard, these are insulators as well. Any things that you would probably not want to, put your hand on if it was hot. Yeah, anyway. Okay, so let's get back to it. This property of our different materials storing and transmitting energy, heat energy in different ways, this principle is called specific heat capacity. And specific heat capacity actually gets referred to in 3 different ways. You have people saying the whole thing, specific heat capacity, and sometimes they just say specific heat, or sometimes they also just say heat capacity. And these all 3 mean the same things. The main differences between this, when people use the term specific heat or heat capacity, is that usually this is based on units, but there's nothing set in stone about that. It's just convention. So usually when people talk about the specific heat, the units for these specific heats will be joules per gram degrees C or joules per gram Kelvin. And for heat capacity, they'll usually use moles, joules per mole degrees C or joules per mole Kelvin. So how is it that we can use either the degrees C or the Kelvin? Let's think about that for just a second. Let's look at the temperature scale between freezing, the freezing point of water, and the boiling point of water. In Celsius degrees, the freezing point of water is at 0 degrees Celsius, and the boiling point is 100 degrees Celsius, right? The freezing point of water in Kelvin degrees would be 273.15 Kelvin. That's why we add 273.15 to any Celsius degrees. And then it would be 373.15 in Kelvin degrees. So our temperature difference between the freezing point and the boiling point is 100 degrees Celsius, or it's 100 degrees Kelvin. So the difference between freezing and boiling has the same number of degrees in between them. And so that means that if we are talking about delta T, which is what we actually are when we're talking about specific heat capacity, we're just going to be looking at the change in the temperature, final minus initial temperatures. And there are the same number of degrees between Celsius changes of temperature and Kelvin changes of temperature. So we can use either the Celsius or the Kelvin interchangeably in heat capacity problems specifically. Okay? So this is starting to tell us that our specific heat capacity probably depends on a few things. I'm just going to say heat capacity because it's shorter. So heat capacity depends on the material and its intrinsic properties, how well heat flows through it, how much material you have, you can see this in the units right here, either joules or grams or moles. And of course you could use any other quantity amount. It's just that these are your two units that you're going to find in tables. And then finally, what the change in temperature is that you want to accomplish. The more change in temperature you want, the more you are going to have to flow the energy in, because energy is an extensive property. Joules is extensive. Heat flow is extensive. Anytime you have an energy unit like joules or kilojoules or calories, we all know that the more candy we have, the more sugar there is in that candy, and the more energy we could get out of it into our bodies. And so that tells us that energy, whether we're looking at it from a nutritional standpoint or from just a standpoint in terms of usable energy for a chemical reaction, energy is extensive. It depends on the amount of stuff we have. So when we're calculating the heat capacity, not the heat capacity itself, but when we're calculating the specific heat, I keep saying the same thing, sorry. The energy flow for heating and cooling is what I'm doing here. So actually, heat capacity does depend on the material, but I wasn't trying to say the heat capacity was trying to depend on the material. This whole thing is the amount, the heat flow to raise the temperature or lower the temperature. That is what's going to depend on all three of these things. So I will instead amend my list to say the specific heat, the heat capacity, depends on the material. And it would help if I could draw my arrow to the right place. Here we go. So if we look at the components right here, the material and how well heat flows in it, that is the heat capacity. And we're going to use a C or a C sub P. The P here is not, well, the P here is for constant pressure. So we can also have constant volume, but that is pretty uncommon in calculation, so we're not going to worry about it. So if we're being generic, we'll just use a C for the heat capacity. And if we want to be fancy, we can be C sub P, which means constant pressure. How much material, that's going to be the grams or the moles of the material. And then what our temperature is, this is a delta T. So our heat flow to raise or lower the temperature, the equation that we are going to find, we're going to use a Q to indicate the heat flow, even though this is the same thing as a delta H. And we're going to have that heat capacity. We're going to have the quantity of the material. I'm going to use M because often it's mass, but it could be moles. And we'll have a delta T in degrees Celsius or Kelvin. So this is our heat capacity. This is our mass or moles. And this is our change in temperature. And for the change in temperature, it does need to be in degrees Celsius or degrees Kelvin. All right, so this is our equation that we're going to use every time we look at how much energy is going to flow into or out of a system based on heating or cooling. So let's go ahead and try some sample problems so that we can see this illustrated. So let's think about a scenario. You decide to make yourself some tea, and you have an electric kettle. So let's say that you put in 500 milliliters of tap water. And we're going to assume that maybe the density here is pretty close to 1 gram per milliliter. And your tap water, it's fairly cool out right now. So the tap water, let's just say maybe it's about 10 degrees Celsius. That's about 40 degrees. It might even be a little cooler than that, but that's okay. You decide you want to make some tea, and you know that you want to boil that water, so the final temperature is going to need to be 100 degrees C. And now you need to know about water. This is liquid water, and if you look at table 6.1 in the book, you'll find that the heat capacity of liquid water is 75.3 joules per mole degrees Celsius. So let's look at this calculation and see what we need to do. Our question is, how much energy needs to flow into the water to boil it? So our equation, Q, that would be the amount of energy, is Cp m delta T. So let's look at our numbers here. We have a volume of water, we have a density of water. Our heat capacity is in joules per mole degrees Celsius. So it looks like we need to find moles of water. Otherwise, though, I think we're okay. We've got our heat capacity in joules per mole degrees Celsius, and we've got Celsius temperatures here, so we'll be all right. So let's work with the moles of the water first. So we have 500, and if you feel confident of doing this calculation, go ahead and pause the video and try it out, and then come back together with us in a minute. If you aren't confident about it, you're not quite sure, that's no problem. Oops, I don't need to do this part of the unit conversion, because I already have my density in gram per milliliter. So I'm just going to go ahead and multiply my volume times my density, and that will get me grams of water. But I still need to convert grams to moles. So let's look up the atomic weights of these elements and convert it to moles. When I looked at my periodic table, I calculated, let's see, where'd it go? 18.015 grams of water per mole. So that means I have 27.8 moles of water. That's a lot, right? 500 grams of water? It's amazing. 1 mole of water is not very big. It's about 18 milliliters. All right, so I have 27.8 moles of water. I think maybe I'm ready to go. So my Q is going to be 75.3 joules per mole degrees C multiplied by my quantity in moles, 27.8 moles, and my change in temperature. So that's 100 degrees C minus 10 degrees C. So this number by itself, that becomes 90 degrees C is my delta T. And this looks like it's going to be a pretty big number. So I'm going to proactively go ahead and convert it from joules to kilojoules. You probably are going to have to do this most of the time. Okay, so when I plug all these numbers in, I get 188 kilojoules of energy that I am going to flow into that 10-degree water from my tap to heat it up to a temperature of 100 degrees Celsius so that it can start to boil, so I can make my tea. Okay, hopefully that seems pretty comfortable so far. But let's go ahead and try another practice problem just to be sure. Okay, so this time let's look at an aluminum cookie sheet. All right, so this is I have these aluminum cookie sheets that I got from my grandmother. I actually had to look because I was curious what they were made out of, and they're pretty worn, by now. But you can just make out on the bottom that it says it's made out of aluminum. So I just went and weighed one, and the mass was 425 grams. So let's say that we take this cookie sheet and we put it inside the oven, and the oven is set to 350 degrees C. Oops, not degrees Celsius, Fahrenheit. That would be really hot. So this is my initial temperature. So I put my cookie sheet in the oven, I let it come to temperature, and then I take it out of the oven and I let it cool to room temperature. So room temperature, let's call it about 70 degrees. That's about what we have in our house right now. And we want to know how much heat energy had to flow out as the cookie sheet cooled. All right, so what do we need? We need to have the heat capacity of aluminum. This is also in our table 6.1. It is 24.4 joules per mole degrees Celsius. Okay, so let's go ahead and try these calculations. Now, notice that these are Fahrenheit degrees, and this is Celsius degrees. So do I have to do this unit conversion before, or can I do it after I take my delta T? Well, let's go ahead and give it a try. Let's try first calculating it and doing this unit conversion first, and then we'll check and see if we get the same number later. So when we do a degrees Fahrenheit to degrees Celsius conversion, if you haven't done this in a while, you're going to take your degrees Fahrenheit and subtract 32 and multiply it times 5/9. And this will give you your degrees Celsius. So let's do it. 350 minus 32 times 5/9 gives me 176.7 degrees Celsius as my initial temperature. And my final temperature, 70 degrees times 5/9. All right, so let's see, that gets us 21.1 degrees Celsius for my final temperature. Oops, let me rewrite that. So my delta T is always final minus initial. And notice here that because we are cooling, we're going to have a negative delta T, and that's totally fine. And we'll come back to that in just a moment. So we're going to have 21.1 minus 176.7 degrees Celsius. And this will get us minus 155.6 degrees Celsius for our delta T. Okay, so this was when we did it, converting these to Celsius first, and then taking the difference between them. So let's take a look and see whether or not we get the same answer if we just take the Fahrenheit degrees. So Fahrenheit degrees, my change in temperature would be 300, oops, excuse me, that's my initial temperature. 70 degrees minus 350 degrees. So that would get me minus 280 degrees Fahrenheit. So can I just convert this to Celsius the way I did before? Let's take a look. If I take minus 280 and subtract 32, and then multiply by 5/9, you can already see this is not going to be equal to the same number that we had before. And so let's take a look at why that is. We just looked at the freezing point of water and the boiling point of water as a way to convince ourselves that our Celsius degrees and our Kelvin degrees were the same size of each degree, right? So in Celsius degrees, we have between boiling, freezing to boiling, we have 100 degrees Celsius. We have 100 degrees Kelvin. So how about Fahrenheit? Well, freezing point of water in Fahrenheit degrees is 32, and it's 212 is the boiling point. So the difference between 212 and 32 is 180 degrees Fahrenheit. So each of these degrees is different. 1 degree Celsius in terms of change of temperature is equal to 1 degree Kelvin, but that equals 1.8 degrees Fahrenheit. So we couldn't just do this change in the temperature first and then convert. But what we could do is we could say minus 280 degrees Fahrenheit. These are a change in temperature degree. And in change in temperature degrees, 1 degree Celsius is equal to 1.8 Fahrenheit degrees. And so if I divide by 1.8, I will get minus 155.6, the way I did before. So this process is okay if you want to do it this way. I would probably find it a little more confusing, and I would stick to this process of convert first and then take the difference. But you can do it whichever way you like. Okay, so let's get back to answering our question. All right, let's see what we have so far. So we're trying to calculate our heat capacity, Cp m delta T. Let's review where we're at. So we have the heat capacity of the aluminum. That's 24.4 joules per mole degrees Celsius. We have the amount of aluminum, that was 425 grams. And we have our delta T, which is minus 155.6 degrees Celsius. So it looks like we need to do a unit conversion again. We have moles here and we have grams here. These are both moles of aluminum or grams of aluminum, but we have to do that unit conversion. So let's go ahead and do that. So you can actually convert either one of these. You can convert your grams into moles, or you convert your moles into grams. Let's actually do the moles into grams this time. So 24.4 joules over mole degrees C. Aluminum has the atomic weight of 26.982 gram per mole, but I want to cancel out the mole. So the mole needs to go on top. 1 mole of aluminum weighs 26.982 grams. So now we can divide this out and get the heat capacity. We would call it the specific heat capacity. So in joules per gram degrees Celsius, the specific heat capacity of aluminum is 0.904 joules per gram degrees C. So let's go ahead and do this calculation now. Q is equal to 0.904 joules per gram degrees C times 425 grams times minus 155.6 degrees Celsius. And this is probably going to be a pretty big number as well. So let's go ahead and divide it by 1,000 to convert into kilojoules as well. So if we do this, we're going to get minus 59.8 kilojoules. This is the amount of energy that had to flow out of the aluminum pan to cool it from 350 degrees Fahrenheit to our room temperature. So notice again, I said I was going to come back to the signs. When we heated water from 10 degrees Celsius to 100 degrees Celsius, we calculated that the heat flow in order to do that was 188 kilojoules. And then we cooled aluminum from 350 down to 70 degrees Fahrenheit. And we calculated that the heat flow here was minus 59.8 kilojoules. So what you can notice here is that if you put in your delta T correctly, this will tell you whether or not you have heat being released, right? Q is the same thing as our delta H, and this is a delta H less than 0. So that means this is giving off energy, and we would call it exothermic. Over here, we have water that is absorbing energy. So my delta H is positive, and this would be an endothermic reaction because we're putting heat energy into the system in order to raise the temperature of the water. One thing I will also point out just briefly for you, right, is the difference between the water and the aluminum. Which one of these required more energy to change its temperature? How would we know that? We would know that by looking at the heat capacities. So the heat capacity of the aluminum was 24.4 joules per mole degrees Celsius, or 0.904 joule per gram degrees Celsius. We didn't calculate the heat capacity in joules per gram over here for the water, but the water was 75.3 joules per mole degrees Celsius. So based on a per mole basis, the water requires a lot more energy than the aluminum does. And hopefully this makes pretty good sense because aluminum is a metal, it's a conductor, and water is not a conductor of electricity. Not unless you dissolve stuff in it, and then it's the stuff that's conducting, it's not the water itself. All right, so hopefully this makes some pretty good sense in terms of how we calculate energies based on heat flow. And when you are looking up heat capacities, these will always be available in tables. So these are not numbers that you need to know or memorize. These are numbers that we just will look up in a table. And I will be posting some tables to our Moodle that are a little more extensive than what's in our book. And I may also refer you to more resources online. And of course, there's always Google if you're looking for numbers.